Wait a second. Okay. Yeah, it's this computer for the slides.
So, good afternoon, ladies and gentlemen. My name is Tomasz Skalski, and I am a PhD student of Politechnika Wrocławska in Poland and also of Université d'Angers, quite near to Paris. I would like to thank all of the people who with whom I discussed this paper, especially to Bartosz Kołodziejek, to Piotr Graczyk, my advisors, and I would like to express my special gratefulness to Ellen Masson. Okay, so my talk will be about connection between the graphical models and the notion of graph Laplacian. So let's start with some basic conventions. During this presentation, we'll consider a simple undirected graph, which will be considered as a set of vertices, of edges between them, and some of these edges will be highlighted as a set of initial vertices, root set. In many cases, it will consist of only one element, so this will be the initial element. The degree of a vertex is a number of neighbors of this vertex. This may be useful. And we focus mostly on the conditional independence. So if we have some random variables or some events, then we may think that some of them should be independent, but in fact, they are not independent in terms of classical independence. So, for example, consider 10 people going for some meeting, and we want to know whether the event of any of them being late is independent or not. And well, these people may not know each other, so they will just go in this rate in which they will want to go for the meeting, but some external event may happen. For example, the train may be faulty and all of them may be late, so there is some dependence. But if we condition their punctuality by the event that this train is not faulty, then we may think that those events are conditionally independent. So in terms of random variables, if when we have the covariation matrix, then the classical independence will refer to the off-diagonal terms, corresponding off-diagonal terms being 0. But in the conditional independence, instead of zeros on the covariation matrix, we consider the precision matrix, which is the inverse of the covariation. which is the inverse of the covariance matrix. There will be also a useful notion of a graph Laplacian. There are at least two definitions of graph Laplacian. So for the convention, we use the 0, 1 definition, for which on the diagonal we have the degrees of the vertices, so the numbers of neighbors, and off diagonally we have -1 when two vertices are connected by an edge and 0 otherwise. So this matrix is non-invertible. So if we want to invert it, then for us it will be useful to add something to the diagonal term. So when we add an artificial neighbor to the root, like the beginning of the graph, then we may just form an augmented Laplacian, for which we add 1 for any root initial vertex. So as an example, on the left we have a graph with one root vertex, which is strictly on the left. It's called 1. We have its Laplacian matrix. So on the diagonal we have 2, 2, 3, 1, 1, and 1. As one can see, the vertex 3 has 3 neighbors. The vertices purely on the right have only 1 neighbor. And in the augmented Laplacian, the first term is called 3, because 1 is then connected not only with 2 and 3, but also it's a root. Okay, so let's start with some examples. So let's begin from the graphs being trees, so the graphs without cycles. Also, we start from an undirected tree with 1 initial vertex. We orient every its edge in the direction from the root. So this way we obtain the partial order on the set of vertices. Then we can define the ancestry of the vertex. So it's the set of vertices which are the ancestors of this vertex, but also with the vertex. So for example, the ancestry of the vertex 5 is the set of vertices 1, 3, and 5. And the cardinality of this ancestry will be the important thing. So here is, this cardinality is 3. We can think about it also as a stage of the vertex, like the number of generation in which the vertex 5 appears. So if we consider the Gaussian random vector with a covariance matrix such that the entry corresponding to 2 vertices will be the cardinality of their common ancestry. So for example, vertices 2 and 5 have only 1 common ancestor, 1. Vertices 5 and 6 have 2 common ancestors, 1 and 3. Vertices 4 and 4, so the vertex 4 has its ancestry having 3 elements, 1, 2, and 4. Then it's exactly the matrix which inverse is the augmented Laplacian. So there is another example which is seen on the screen, and also this theorem is true for every graph being a tree. So then we can ask a question: what will happen in the case when we have when we add some cycles to the graphs? So also the inverse of the augmented Laplacian for the cycle graph is known, is proved. So there we have every entry being having at least one. So it's like we start in the root, but also there is an added number which depends both on the distance, one-sided distance from one and distance counted from the second side. And for clicks, such matrix is quite more visible. So on the one we have 1. On the diagonal we have 1 plus 2 divided by n, and of the diagonal we have 1 plus 1 divided by n. It's also counted for daisy graphs, which can be thought as a connection between a complete bipartite complete graph and the complete graph. So this is a graph which has its internal part. This internal part is a complete graph, and it has its external part, which consists of vertices which are independent, but they are independent only if we condition it by the interior of the daisy. So on these examples, we have the internal vertices on the left and the external vertices on the right. So we can think about the graphical model with underlying graph being a daisy graph as a series of some internal factors which are connected somehow, and the set of independent external factors which can modify the system of events. So this is also a sum of the complete graph with internal vertices and the complete bipartite graph connecting interior and exterior. Okay. Here the augmented Laplacian can be defined in many ways, because there are many ways how to choose the root. So here are the inverses for quite classical cases, like one vertex inside, all vertices inside, one vertex outside, and all vertices outside. Okay, we can also connect the Laplacian graph with the discretized Wiener process. So, for example, if we have a Wiener process, just the classical one, we can consider just the events in the Wiener process during the integer times. So W1, W2, W3, and in the middle we have its covariance matrix, and it looks that it's coupled with a path graph, also with the notion of augmented Laplacian being the inverse of the covariance matrix. Then we may also see that the tree is connected to the branched Wiener process. So until some time we have the same Wiener process, but then we branch it to independent winner processes. And it behaves the same. And there is also a connection between Wiener bridge and the cycle graphs. Because the cycle may be considered as a path, but only if we assume that at the beginning of the path and at the end of this path we have purely the same point. And we can just see that for the cycle graphs, we have exactly the same thing as the same covariance matrix as the covariance matrix of the Wiener bridge. And I see that the time is finishing, so I will finish the talk with questions, some discussion for the future about how to generalize these examples to the broader classes of graphs. So maybe it will be possible for every graph, and maybe with this accent, I would like to thank you for listening.
Does anyone have a question? No. So on the Zoom there is a question. No question. Frank, do you have a question or?
Not especially. Is there any question in the room?
No question in the room. So me, I have a question about what is basically the motivation. Like you want to find like a stochastic process who has the graph Laplacian as the augmented Laplacian as a precision matrix, or do you have like motivation for like real data that follows those stochastic process, like your quotient process with the covariance matrix as intersection, the cardinal of the intersection of the ancestors? I don't know if I'm here.
Thank you for the question. I have to admit that I'm mostly motivated to this problem theoretically.
Mm-hmm.
Like I moved to this part of my PhD from the graph theory, okay. So also with some notions from random graph theory, and also like for me it looked quite natural to connect it with this Laplacian matrix.
Okay.
And to see them. Nice properties.
Thank you. If you have a question?
Maybe you have some nice result about L star, but maybe a way to extend in the examples that you have, for instance, only for the tree, for instance, to replace the graph. You are taking a very special graphical model with a special intensity matrix, but maybe it's possible to have a more general graphical model on the same graph. Is it possible to keep something of the structure of the L star of G that you have, putting other parameters, because you have been putting the covariance in a very special way, but the covariance maybe by this nice trick to add a one somewhere, you can land on something interesting. Have you tried to use that trick on more general matrices than the Laplacian of graph?
Merci beaucoup pour cette question. I think this can be combined with with weighted graphs when there is
Exactly.
when there are the weights on both vertices and edges, and also on weighted roads. I thought about it for some time, but so far without the exact results. So
The weights
this
must
will
be always one.
yeah. So
Because
this,
in graph theory, you have many circumstances where you can replace a theorem with a weighted graph and you get something very simple. Okay, thank you.
So thank you again, Thomas, for this talk. I invite Jan Caban to present his talk about